NHK 技研、東京にある NHK 技研のサンクリングダーです。ちょっと、so I'm going to do this in English, if that's the plan, I understand. So this course is 2 lectures today and tomorrow, and then there's some practical exercises next week, next Wednesday, I think. Introduction to Pattern Recognition is the title of the course. It's in 3 main sections, which are feature extraction, pattern classification, and finally machine learning. I've got rather a lot of slides, so I won't be spending a lot of time on each slide, but I'll be skipping stuff. You don't need to know it all, you can just use it as reference material. Okay, so I'll get straight on with it. So pattern recognition, well, what's a pattern? In the most general sense, it's some kind of irregularity in data as opposed to noise. So we're trying to recognize structures of some sort in data. The data itself could be discrete, continuous, could be of however many dimensional support. For example, a one-dimensional time series. Images are obviously 2-dimensional, videos 3-dimensional, etc., etc. And the data could be it could be quantized, it could be integer, it could be floating point, it could be anything. Okay. Here are some examples of some patterns, trivial examples. A DNA sequence is a one-dimensional sequence with rather few symbols in its alphabet. Here's some handwriting, which is kind of nearly 2-dimensional. Here's a signature. Signature recognition is quite a big thing in potentially for verification of financial transactions and so on. I don't know if you can read this signature. This is Barack Obama signature. I haven't got Donald Trump's signature, but it looks like this. Okay? I don't know if you've ever seen Donald Trump's signature, but it's like this. Anyway, this, however, is not actually Donald Trump's signature. It's a seismogram, so of earthquake earthquake appearing to be imminent. You get these waves up front that you might wish to recognize in order to stop the Shinkansen and turn the power off and this kind of thing. So here's another 1D. Here's a 1D time series, like for audio or speech, which you might be wishing to recognize. Fingerprints, obviously. Iris recognition is getting quite common because it works very well. Irises are very individual. So for authentication of people's identity, iris recognition is actually about the best you can do right now. Face recognition, of course. This is a bit before your time. This is Hatoyama Yukio, who was a big politician a few years back. Here's a 2D time against frequency spectrogram. Blood vessels in the back of the hand here that can be used for recognition. This is a video of people at an airport, and one of the things that people want to recognize is unusual or suspicious behavior. People putting down a bag and walking away, for example. Here's gait, which is how somebody walks, because that's actually quite individual and can be used for recognition. Okay, so those are some typical examples. Application areas include coding and recognition and retrieval of text and image and video, such as image and video coding for transmission, compression for storing images on disk, and for retrieval search. Archive indexing, this is something where I work at NHK. They have lots of archives, being a TV company, and we would like to be able to label all the archive video automatically using recognition technology so that we can then search it much more quickly. Data mining, duplicate detection. This is for things like detecting copyright violations. Speech recognition is a big field. Subtitling, text entry, user interfaces, and written text recognition for sorting out the mail. Optical character recognition is another big field. Medical screening, a lot of image recognition research now is directed towards detecting, for example, cancer cells in a background of healthy cells, assisted diagnosis. Biometrics and security is the other big area. DNA testing and matching, face and iris and fingerprint and signature and gait and what have you. Detection and recognition and verification of all those things. Detection and recognition and verification are not quite the same thing. The applications are all slightly different, which I'll say something about later, and abnormal activity detection, like at the airport. Okay, so first main section of the course is feature extraction. You will probably be aware that deep learning has become more and more important in recent years, and so traditional methods of feature extraction followed by classification have lost some of their glamour. But one of the problems with deep learning is that it needs a lot of training data, and there are situations where you don't have a lot of training data, so you need to, in that case, you need to know about feature extraction and pattern classification, because you can't rely on deep learning to automate that stuff. So here's some examples. Traditionally, back in the good old days, features were linear, and one of their uses of feature extraction was to reduce dimensionality, still is. So here's a couple of images. Here's NHK's logo. It's made of pixels. There's pixel I and J, so I is the vertical and J is the horizontal coordinate. Here's a nearby pixel, and you could surmise that the brightness values, the RGB values of these pixels, are probably very close or maybe identical. Similarly here, you've got two pixels close together. You could guess that the RGB value's pretty similar, maybe not identical for a natural image. But so we regard images as a several thousand dimensional vector of pixel values. Nearby pixels, because they're generally similar, transmitting all the pixel values independently is kind of a waste of bits. It's inefficient, and if you look at to take the extreme example, an 8K super high vision video at 60 hertz frame rate is 48 gigabps, and you don't want to be transmitting that or storing it if you can help it. So we aim to reduce the redundancy in the signal, which raises the question of what kind of features should you extract and code. In this trivial example, you could, for example, say, well, we'll transmit, for each row, each scan line, we'll transmit the value of the first pixel, and then if all the rest are the same, we'll just say repeat it 512 or 1,000 times, which is a thing called run length coding, which is actually a thing. But in general, you might ask whether there's a mathematically good or best way to do it, depending on what you're trying to do. So most low-level image processing is still based on the old kind of hardware model of convolution of linear filters with input images. So here's an input image consisting of pixels f of ij, and here's a filter mask consisting of a bunch of filter tap values, and for the output at this point, g of ij, is going to be this pixel value in the middle multiplied by the weight of the corresponding filter tap, plus this tap times this image value, this tap plus times this pixel, plus this tap times this pixel, etc. And that gives you your output. You scan this window, this filter over the whole image to get your processed output. That's the simplest model of a feature extraction from images. Normally we use matrix vector notation, so we don't have to write sums or integrals everywhere. So in this case, here's our image pixels stacked up into one big vector, n-dimensional vector over here. Rn is an n-dimensional real vector space. And this here is a matrix transformation. Matrix is A. We tend to use the transpose here for various reasons. So this is an m by n matrix which transforms this n-dimensional signal vector into an m-dimensional feature vector. And usually m can be is less than or equal to n. Not necessarily, but usually. Then we'll transmit or store or whatever we want to do with our data, and then at the back end we'll do some kind of signal reconstruction to be specified later, probably by something like an inverse transformation of this, depending what the application is. So we're representing data as a real-valued n-dimensional vector x, which is, for images, that's going to be a big stack of all the pixel values in one vector. We tend to remove the mean because there's no point coding and transmitting the mean every time. We just add it back in at the end. And we extract these m features in a vector y through this linear transformation A, or A transpose here. So if m equals n, so if this transformation matrix is square, then the transformation generally can be invertible, so you can recover, in principle, you can recover the original signal exactly. You might want to do that in order to, for example, treat these different components differently, allocate different numbers of bits to them or whatever. Okay. If, however, there are fewer features than pixels, the transformation is not invertible. It's said to be lossy, and that achieves dimensionality reduction because m is less than n. So you're extracting fewer features than there are pixels, which raises the question of what are the most relevant features to extract from irrelevant data and noise, so as not to waste bits transmitting and storing them. Here's an example of a typical face recognition system where we extract some kind of features from the input. So here's the world, here's a camera pointing at some part of it. We'd probably do some processing, pre-processing, filtering, normalization on this guy's face. Do some kind of feature extraction, and that will give us our feature vector. So this is going to be the transformation that we just saw in the last slide. And this will give us, for every image that we put in here, this will give us a vector which we assume is going to land somewhere in this feature space, so-called here. And in order to do something like face recognition, we have to compare the red dot here, which is our the feature vector that we get when we put this guy's face in, with these other data which are pre-registered feature vectors corresponding to, this is person A and this is person B. So in this case, these blue crosses are all for person A, green pluses are all the data that we've registered for person B, and if this guy's feature vector lands there, you could take a guess that it's more likely to be person B than person A. So hello person B, and we've recognized person B, hopefully. So that's a fairly typical example of, in this case, our feature space looks like it's actually only two-dimensional, despite this image here being probably several thousand pixels. So this is an extreme dimensionality reduction going on here. So is there in some way, a best way of doing this mathematically? The answer is yes. Given that you have a linear system like this, where you're trying to extract some feature vector from a linear transform of your data. And the method is called principal components analysis. You may know about PCA already, but it's a classical statistical method. And the idea is to extract those features that best express the amount of variation, or the way in which the input signal varies. So assuming that we get our feature vector through a linear transformation like this, after subtracting the mean here, which is this thing here. The capital E here is the statistical expectation or average. So this is just subtract the statistical average of the input vector. There's a thing called a covariance matrix. Now, I don't know how many people are familiar with covariance matrices. Anybody? Yes. Excellent. Right, one person at least is familiar with covariance. Okay, so a covariance matrix expresses how the components of a vector covary with each other. So knowing one component, how much information does that give you about any of the other components? And it's expressed as this thing here. So here's our vector y, our feature vector. This is a so-called outer product of y with its transpose, and then you take a statistical average expectation here. So this matrix expresses how much each component of y varies with each other component. And you can express y's covariance matrix in terms of x's covariance matrix, the input signal's covariance matrix, and the transform matrix A, like this. What's the point of doing that? It is that if you choose your transform A to be made, the transform matrix to consist of the top m eigenvectors of your input signals correlation matrix, like this, then it turns out that the correlation matrix of your feature vector is diagonal, meaning that it has non-zero, in fact positive values on the leading diagonal and zeros everywhere else. And that means that the different components of your feature vector, your different features, are uncorrelated with each other. Why is that a good thing? That's a good thing because if they're correlated with each other, then you waste bits transmitting both of them. If you can uncorrelate your various features, then you're not transmitting redundant information by effectively transmitting the same information twice. Okay, so moving on. The way that looks in pictures is like this is an example of a two-dimensional signal vector, components x1 and x2. And here's a load of data, these blue crosses. And you can see from this, the way the data's spread here, that there is a significant correlation between x2 and x1. When x1 tends to increase, x2 tends to increase as well. If we do the principal components analysis of that, we find that the principal components are A1 and A2 here, and you can see that A1 here spans the longest axis of the so-called inertia ellipse, which expresses the correlation matrix of the original signal, and A2 is the smaller axis, the minor axis of that ellipse. So having transformed x1 and x2 into a new vector, y1 and y2, y1 and y2 are not correlated with each other. You can't predict anything about y2 if you know the value of y1 and vice versa. So they're uncorrelated with each other, unlike x1 and x2. Okay. I'll skip over most of this. Just the one thing to say here is the reconstruction. Having done this transformation, if you want to reconstruct the original input x, we put a hat over it for estimates or reconstructions. We reconstruct that by adding the original mean back in again, and then these yi are the components of the feature values, and the ai here are our feature vectors, which are the eigenvectors of that correlation matrix. Effectively, what this does is it projects the data here. This is a three-dimensional signal space, and we're extracting two principal components from it, expressed by this ellipse here. And you can see from this picture, effectively what you're doing is projecting each of these data orthogonally, that's perpendicularly onto that subspace of the signal space. Okay, you don't need to worry too much about that. This is an example, an old example, is about 30 years old now. One of the first face recognition systems was the so-called eigenfaces. And the way this works is, say you're given a set of faces that you wish to build some kind of principal component space out of. So we've got P of these training face images. As far as possible, they're aligned so that the eyes are in the same place in each image and so on. So we take the mean out. That's this image down here. This is the mean of all these images. And then calculate the principal components. This is the biggest one, which you can see, I think, if you recreate, I'll just go back to the previous slide, if you recreate a face as a weighted sum of these components like this, so you've got the mean plus a certain amount of each of these principal components. So here's the mean plus a certain amount of this image plus a certain amount of this image plus a certain amount of this image and so on is the reconstruction. You can probably tell that this image, if you add some of this image to the mean, it's going to make this area lighter and these darker areas darker and so forth. You can see also that the features slowly get more complex as you get into the higher orders up here. The bigger principal components tend to emphasize gross features, and the higher value ones tend to emphasize small differences in the data. Okay, so the way the system actually works, this is just one little trick that can be done, needs to be done, is that if you try to actually calculate this covariance matrix of your input signal here, for even a quite small image like 128 by 128, your correlation matrix is 16,000 by 16,000, and you really don't want to be computing the eigenvectors of that. Instead of calculating the eigenvectors of this thing, xxt, you can calculate the eigenvectors of xtx, which is much smaller, and recover the same eigenvectors that way. Just mention that in case anyone ever decides they actually want to implement this. To actually use this kind of system, each of the faces that you've registered, the kth face will be RK. We're going to represent that by a corresponding m-dimensional feature vector yk of these principal component coefficients, projection coefficients. Each of those is the inner product of this input vector with one of the eigenfaces, the corresponding eigenface. Okay, so we're going to represent a novel input face R dash then by another m-dimensional vector y dash, which again is the input, the inner product of this input with each of the eigenfaces, like so. And then you recognize your novel input face R dash by finding the nearest neighbor, for example, of y dash among all the yks, which are your principal component vectors for each of your registered faces. So in pictures, it looks like this. So here's a training set for you to build your face space out of, calculate the correlation matrix, find its eigenvectors. So we do that, we retain the top however many we think we need to do the recognition. It happens, if you get down into these higher order eigenvectors, actually they're almost more noise than signal. So it's usually better to use the top few rather than, you certainly wouldn't want to use all of them. Okay, so we build this so-called face space from the mean and these various eigenvectors. and then we've got a bunch of people here who we want to recognize if they appear in the input. So now this set can be the same as this set. It usually is, but it doesn't have to be. So for each of these faces registered in our database, take all the inner products of that face with all these to give you a projection vector yk. Then for an input face, r dash here, we're going to do the same thing with that, take the inner product of that with all these, get a vector y dash, and compare y dash to all our various yk from the registered faces. And whichever is the nearest in some sense, that will give us our result, recognition result. So the eigenface system is only ever used these days as a training, as an academic exercise, because it doesn't work well enough under most circumstances to be useful. Although principal components analysis is used more widely. So what is a good feature? The answer is that for classification, good features depend on the task, and they should be robust so that they should be similar within each class. So for example, all views of a single person's face with different lighting conditions, different head angle, different facial expressions, and so on, ideally should give you similar feature values, and the values for different people's faces should be significantly different if possible. So if these apply, then you'll hopefully end up with something like this, where the feature vectors corresponding to the different classes are easy to separate. If it doesn't go quite as well as that, you might end up with a multimodal situation like this. You may end up with a non-linearly separable situation like this in your feature space, or if you luck out totally, you could end up with something like this, which is essentially impossible to separate. So you want to avoid doing that. This is an example of that. In face recognition systems, errors tend to come from differences between the situation under which you registered people and the situation in which they appear subsequently in front of the camera. So we'd like it to be robust to camera variations, using a different camera from the one you used to register people, lighting variations, indoor and outdoor, sunlight, outdoor sunlight is particularly nasty. Aging, if you register somebody and then 10 years later you try to recognize them, that's difficult. Makeup, facial expressions, hairstyle variations, sunglasses, etc. And 3D head pose, the angle of rotation of the head, is a big issue. Here's a trivial example. Here are two of the images in our database, and here's an input image. And if you just do a naive pixel-to-pixel comparison, you could guess that probably this is the closest database image to the input, whereas in fact that will give you the wrong ID, and this woman is in fact this woman here. So that's a trivial example of where lighting differences and three-dimensional pose differences can cause trouble. So the way to get around this traditionally has been to try and use invariant and robust features. One approach is to try to extract the shape of the face, because if you can do that, it's not going to depend on lighting so much. If you can extract the face shape in a fairly lighting independent fashion. So a system, this dates from the mid-90s, this system. It's still used to some extent in commercial face recognition systems for pre-processing more than the whole system. But anyway, what it consists of is a number of points anchored to the face at which various feature values are locally computed. And then this is called an elastic grid, because as the face distorts, you can fit this grid to the face and try and find the so-called these are called fiducial points, to try and map your grid to the person's face, so that, for example, you can handle non-frontal poses like this, so on. The most invariant thing you can get is 3D shape. If you can actually do a full 3D shape reconstruction, that's going to be the most invariant to things like head pose and lighting. But that's computationally difficult, requiring stereo cameras, and is not usually feasible, although there is some work on that. For biometric verification, as I said earlier, actually features like iris and fingerprint recognition are more reliable than face recognition, even with features like this. But they are more intrusive. Obviously, you have to get closer to people for that to work. Okay, feature extraction. There are some examples. This is the textbook, nominally the course textbook. It's quite old now, but there really aren't very many good general pattern recognition textbooks around. So it's worth reading that and maybe something a bit newer. So here's a kind of dumb industrial vision task, trying to classify images of fish here. Here's some fish into two classes, salmon and sea bass. We're assuming that we've only got these two classes, and we're given a set of labeled training data. This is a bunch of salmon, this is a bunch of sea bass. We need to deal with unrelated variation like lighting, the angle of the fish in the image, and so on. So that's a typical image, input image to this system. So, well, how about, for example, using the length of the fish, if you can measure that from the image? Turns out not very good. If you try to do that, you find that the salmon are mostly about this length. This is length on the, I don't know why it says count. Oh, it's because it's a histogram. Okay, so this is length here, and that's the how many fish are that length. Most of the salmon are around 10 whatevers long, but some of them are much smaller, some of them are much larger. Similarly, sea bass are bigger on the whole, but there are some very small ones and fairly big ones as well. The distributions overlap quite badly, which makes it a difficult problem. This choice here, this dotted line of a threshold, if you were to say, right, anything that's less long than that we'll call a salmon, anything that's longer than that we'll call a sea bass. If you do that, you minimize the number of errors on your training data, but there are still a lot of errors, so it's not a great feature. Well, how about using the lightness of the scales instead? If you look at a histogram of lightness of the scales, it's a bit more well separated than the length feature, but not that great. This choice of a line here, threshold, will minimize the error, but still gives you quite a few errors because you've got salmon that are lighter than that level, and you've got some sea bass down here that are less light. How about if you use both of these features together? So here's a two-dimensional feature space now, and instead of just using lightness, i.e. drawing a vertical threshold, or just using the width here, drawing a horizontal threshold, you can draw this linear threshold at any angle that you like. And if you put it there, this minimizes the error, and you get fewer errors on your training data than using either of these axes features alone. And you can see that if you rotate the space, it amounts to projecting your data onto this red line here, so that you have a single index, y0 here, and anything above that has a y0 above this point up here, call a sea bass, anything below, call a salmon. And that will work better than either of those alone. So this raises the question of how should you choose a simple linear decision boundary like that? And one answer to that question is a thing called linear discriminant analysis, LDA. It's important to say this is not the same as principal components analysis. The criteria are different. First of all, we've got labeled classes. We have two classes of labeled training data, and the idea is to find a line onto which projecting that data gives you the best separation, gives you the best chance of doing the classification. So here is an example of this orange line. If we put it here, the line has to go through the origin, by the way. That's rule number one. If we project all these data onto this line, you can see that the projection of the green pluses is quite nastily, badly overlapped with the projections of the blue crosses. Whereas if we put the line here and project the data onto it, we get a nice cluster here from the green class, and a nice cluster up here from the blue class, and they're quite well separated, so that's probably going to work much better. And it turns out that you can formalize this mathematically. You only need to worry about second-order statistics, the correlation, and we maximize this fraction here, which is mu1 and mu2 here are the projected means of each of the classes. So taking this example down here, here's our class number 1, and the projections are these blue dots here, and their mean projected onto this line is this blue dotted line here. Similarly, the projected mean of this class projected onto here is this mu2 here. So the wider that these are separated, the better. And what we don't want is the scatter, S1 and S2, of these two classes to be large. Ideally, we like the scatter to be nice and small, like this. So here are the two class means. We're looking at the difference between them squared, and here are the scatters, the sum of the two scatters there. Formally, you don't need to worry too much about the solution, but to cut to the conclusion, here's the squared difference between the two means. Turns out to be given by this. This is a quadratic product involving, here's our linear discriminant, the line V, and this SB thing here is the so-called between-class scatter matrix, which is defined here. It's an outer product of the difference between the two means. Okay. Then on the bottom of that fraction that we're trying to maximize are these scatters, which you don't need to worry about all this stuff. But the bottom of that fraction, if I just go back to that, the bottom of this fraction here is the sum of the two scatters, and that's given by this thing, which is another quadratic product between our vector V and this within-class scatter matrix, which expresses, it's actually the sum of the scatters of the two classes. Okay, so the solution to minimize that fraction is this. You don't need to worry about this, but it reduces to a fairly simple eigenvalue problem like this. And finally, if you solve that, the solution is this thing. This is the inverse of the within-class scatter matrix, and this is just the vector joining the two means of the two classes in the original signal. So it's a pretty simple linear classifier. So it fixes the problem that a naively selected projection direction with even if it's got widely separated class means, which is good, that may not be best if the scatter is not the way you like. So for this example here, on the horizontal axis here, we've got nice large separation of the means here, but the scatter of each class is such that they overlap on the horizontal axis more than they do on the vertical axis. So that's an example where LDA works quite nicely. It will give you a line probably somewhere up here. It fails in cases where the data isn't very Gaussian, or where all the information determining the class differences is actually in the scatter and not in the means, like this, where both classes have a mean right in the middle. Same with this and same with this, but this is not means right in the middle, but the classes are overlapping. Okay. A little word about image features before we get into the classification stuff. Going back about 30-something years, I guess, people used a lot of linear texture descriptors like Fourier transforms and wavelet transforms to describe image features for classification. This is probably the most famous image used for image processing experiments. The reason this was popular, apart from some reasons that may be obvious, is that it has a bunch of high frequencies down here. It's got a face in it, and distortions to the face are the most visible kind of distortions to human viewers. It has a bunch of high frequency stuff down here, textured high frequency stuff. It has a lot of sharp boundaries. So from a signal processing point of view, it's a good test image. So you'll still see this image used now, despite it being 40 years old. These are examples of edge detector outputs. This is a vertical, horizontal, beg your pardon. This one's a horizontal diagonal edge detector. And here are the energies extracted from these two edge detectors here. This is a so-called canny edge detector, and that came out in 1986. So this is quite old, but a lot of traditional image processing has used features like this, linear edge detectors followed by some kind of non-linearity. Gabor wavelets are another fairly commonly used feature, even now. What we have is complex exponentials like this, which are basically sine or cosine grid patterns with a Gaussian window around them so that they don't go on forever. And if you convolve one of these with an image, you can extract how much of frequencies near that spatial frequency are in each image patch. Typically, you use a whole set of these things like this, all different sizes, different orientations. And if you look at the Fourier transform of these filters, they give you this kind of partitioning of your spatial frequency space. If you're not familiar with spatial Fourier transforms, don't worry about it. Okay, so these features have been used. The fact that they have a phase, there's kind of a cosine and a sine version of each of these filters, and that allows you to estimate physical displacements between, for example, some point on somebody's face in the database and the same point in an input image, so that you can do the alignment between the two by measuring the shift and taking it out. Okay, so-called HAR or HAR-like wavelets, these have been around since about just after 2000. These are very simple features which express the difference between average brightnesses of rectangular regions like this. This method, Viola-Jones, was the original ultra-fast face detector that was popularized by what used to be Intel's OpenCV computer vision library. And it uses a large number of these features and then trains a classifier to decide which ones are useful and which ones aren't. The great thing about this system is that these features are very fast to compute, and the system forms a kind of a cascaded classifier so that you can very quickly reject images that don't appear to be faces. So, for example, the first feature might be this, where the feature value is the average brightness of pixels in this white rectangle minus the average brightness of pictures in this dark rectangle, pixels in this dark rectangle. Because statistically this area is on average brighter than this area here, if you don't pass that test, you can instantly reject this region as a possible face. So it's very quick to reject non-face images. If it passes that test, then you go on to the next, more complicated feature. For example, is this region here lighter than the average of these two, or whatever? So, and you gradually, these features get more complicated until you are reasonably confident that you have a face. Okay, so one of the advantages of these kind of very simple features is they're very quick to compute. These Haar wavelets, you can use a thing called an integral image, which is a convenient trick. Integral image is an image where for each pixel, the value there is the sum of all pixels to the top and left of it in the original image. So here we go, yeah, sum of pixels in the rectangle from the origin, which is up here, to whatever point in the image you're at. So you can compute this very quickly, recursively, like so. And then if you want to retrieve the average pixel brightness in this rectangle, for instance, you only have to access the integral image at these 4 locations, A, B, C, and D, and then do this quick sum, and you get the average brightness of this rectangle in the original image. So it's very quick, and it allows you to compute features like this very quickly. Okay. Another quite popular feature is local binary patterns, which this expresses differences in brightnesses in a very local area around some center pixel. So, for example, here we've got a bunch of darker pixels separated from what's probably an edge from a bunch of brighter pixels. And looking at the distribution of these kind of features can be used for face recognition. This kind of local comparison of pixels, because it's a local comparison, it's invariant to things like monotonic transformations like luminance. So if you increase the brightness of the whole image, these features don't change. So it's more robust than some other features. Okay, moving on. Histogram of oriented gradients is another feature that's become popular. This is about, 15 years old. In this kind of feature, you look at local image neighborhoods and look at orientations of the image within each of these neighborhoods. These also tend to be quite invariant to monotonic transformations like luminance, and to a certain extent dilation and shifts, translations and rotations of the image. You don't need to worry about all this, but here's a typical example. This kind of feature is often used for pedestrian detection, trying to detect people's whole bodies appearing in camera images like this. A lot of this kind of feature has been used for self-driving cars to detect pedestrians stepping out into the road, for example. So here's, you can see some, this image here shows the strongest orientations here measured around the body of this guy here. We tend to put all those features into an SVM, which is a support vector machine, which will classify whether it thinks this region is a person or not. We'll cover support vector machines later. But this is still a fairly popular feature for pedestrian detection. And the last one that I would like to mention is the so-called scale invariant feature transform, or SIFT. This has been around for about 15 years as well. And this, again, is another kind of image neighborhood feature. There's a bit of Gaussian blurring applied to get rid of noise and so on, and then a difference of Gaussians essentially it's the same as a kind of a bandpass filter. It gets rid of the average brightness and then gives you the kind of local image activity at some level of resolution. And then local extrema, local maxima and minima get detected, and a number of key points are extracted, which can then be compared with the same features extracted from other images. And these are quite invariant to some kinds of shifts and rotations and so forth. Here's an example of various image neighborhoods with a descriptor, so-called key point descriptor, calculated at each cell like this, and putting these descriptors together, you get a kind of a histogram of what's going on in each local image region that can then be matched with the same kind of feature computed from a database. Then this is an example of matching using these SIFT features. Here's a target image, and here are 4 local images that we want to find in this target image. They're taken from a slightly different camera viewpoint, and it's quite a difficult matching problem. And here are the 4 regions found, the outer rectangles. Show you these regions found. This one here, I think, was, let's see, this totem pole here is this 90 degrees rotated, and so on. So these features have been used to try and do rotation invariant matching and scale invariant matching. Okay, that's enough about image features. Next part of this course is classification, the second of our 3 parts. We tend to, you've already seen in some of the earlier examples, things called decision boundaries, which are lines that separate, lines or hyperplanes or surfaces or whatever, that separate ideally our classes in our feature space. So we classify a novel input pattern according to the location in feature space of a feature vector extracted from it. And just to go back to this example, here's a feature space here and a decision boundary in this feature space that separates these 2 classes. Probably going to be some kind of surface down here. It might be a straight line if you're very lucky, or it might be a slightly more complicated curve. But that would, a decision boundary is the boundary between our classes, and locating them well is the key to success. So we just skip one there. Yeah. So these are locations in the feature space where the assigned classification changes from one class to another. They depend on statistical models of the input and training data and performance criteria, including how fast you need to go, how much memory you've got, and what the relative costs of different errors are. So classifying an A as a B may not be bad as classifying a B as an A or whatever. So those things will affect where we put decision boundaries. So there are a number of different ways that you can do this. I'll just go on to the next slide first. Here are 3 different ways of splitting up a feature space. So here we've got a training set with examples of little a's, little b's, and little c's. Now, these are examples. So each of these is one vector, one feature vector. In this case, big A here is the centroid, the center of gravity of these A's, these 4 A's up here. This big B is the centroid of these B's. This C is the centroid of these C's here. And if you put a line centrally between each of these centroids, you get a split of the space like that. Alternatively, you can draw decision boundaries like this that separate all the classes. So all the C's are in this region here, all the B's are in this region here, and all the A's are in this region up here. So this is an example where you might assign nearest neighbor, NN is nearest neighbor. You might assign an input here to the nearest neighbor class, which is A in this case. Here you might assign it to the nearest centroid, the nearest class centroid. If you do that, you're going to get, your answer is going to be B. Here you might assign this input to the region that it's in, having chopped up your feature space like this. And this is a kind of a definition boundary. And in each of these cases, you get a different classification of the same input. So going back a slide here, exemplars, these are for example, if you use the nearest neighbor to classify an input. Prototypes uses for example, the class centroid or mean to classify a novel input, and some boundary defined by planes or polynomials or parametric model of your data can give you a situation like this one over here. So those are different examples. There's a maximum of how well you can do with a classification problem, and it's called the minimum error or Bayes classifier. So if our problem is to assign a feature vector x, which is a d-dimensional vector, to one of C classes, here are the classes from 1 to C, called omega I. We define a set of these functions, one for each class, gi of x, and we're going to assign our input vector x to that class for which the discriminant function is maximum. So the mth discriminant function is bigger than all the other discriminant functions at that value of the input vector x. And if you set those discriminant functions to be this thing, this is a posterior probability. I don't know if you're familiar with conditional probabilities. Maybe some of you are and some of you aren't. But this thing, P of omega I, this is read as given. So P of omega I given x. So this is the posterior probability, the probability that the given value of x came from the ith class, omega I. And if you set your discriminant functions to be these posterior probabilities, assuming that you can estimate these from your training data, then it can be shown that you will do as well as you can on any classification problem. This is just proving why. No need to worry about that. That's not unique, though. Although you can guarantee doing as well as you possibly can, there are other discriminant functions that may do as well. One of them is to use, instead of this posterior conditional probability here, you can expand that using, this is a thing called Bayes' rule. So the probability that given a piece of data X, it came from the ith class, can be represented as this fraction here. And now we have on the top here, we have the X and the omega I are the other way around. So this is a thing called the likelihood, and P of omega I here is the prior probability of any data coming from the ith class, and on the bottom here is the probability distribution of the vector X, which you don't have to worry about because that's the same for all classes I. And so you can set your discriminant function here to the top of this fraction here, P of X given omega I times P of omega I. So this is the likelihood times the prior probability of omega I. And that will give you the same ranking as if you used the posterior probabilities. And it will therefore be maximum for the same class, omega m. You can also take the log of that if you like, because log is monotonic transformation. So if you take the log of something, the ordering of the various classes doesn't change. And so if you set your discriminant to be this thing, the log of this likelihood, probability of X given omega I, the probability that this sample came from the ith class, plus the log of the prior probability of the ith class, because not all the classes may be equally probable. This is more convenient usually, so people tend to use this form. It also separates the likelihood, the dependency of the data on which class it comes from, and the prior probability of each class. Okay, so what that looks like in practice is, for example, if you've got a couple of classes which have probabilities that look like this, putting a decision boundary in a place that separates those as well as possible will give you something like this. It's projecting these probability distributions down onto the bottom here. Here's, if anything, if a data point falls in this middle region R1 here, we will assume that it came from this class, omega 1, and if it falls out there or out here in region R2, we'll assume that it came from this class, omega 2. And if we put those decision boundaries in the right place, according to this, then we will do as well statistically as we possibly can on this problem. Okay, the shape of these decision boundaries is going to depend on the shape of these probability distributions and on the prior probabilities of each class. At this point, I used to put a whole bunch of slides in about the different shapes of decision boundaries for different probabilities, but you don't really need it. So I've reduced it to this slide here. So using the log form of the discriminant like this, so our discriminant function for the ith class is the log of the likelihood, which is the probability that a particular datum came from the ith class, plus the log of the prior probability for that class for each of these classes I. Here's a Gaussian, or what looks like a Gaussian. So this is a rather typical model. These probability distributions look very much like Gaussians, and it's usually, quite often, a good model for quite a lot of data in real-world situations. In that case, the probability of x, given that it came from the ith class, is going to be a Gaussian shape centered on the mean mu I of the ith class. So this is the center of that class, and the shape of that distribution is determined by this thing here, sigma I, which is the covariance matrix, which we met back when we were talking about principal component analysis. So depending on the covariance matrix, your Gaussian could be circularly symmetric, or it could be elongated in some dimensions. So if your likelihood function for the ith class looks like this, then the discriminant function, which we've defined up here, is going to look like this. When we take the log here, the exponential here disappears, and we end up with this quadratic product. This is input vector minus the mean. This is the inverse of the covariance matrix for the ith class. So this is a quadratic product. This thing is, this is a constant that doesn't depend on the class, so that disappears from comparisons between the classes. This is the covariance matrix for the ith class, and this is the prior probability of the ith class. So comparing, for a particular value of our data vector x, comparing gi of x for all the classes I and picking the largest one will give you the best classification. And boundaries for typical data distributions can be very simple, hyperplanes or lines, or they can be more complex depending on the shape of the covariance matrices. Okay, that's enough about that. A very commonly used and probably the simplest classifier is the nearest neighbor classifier, which is what it says. So you classify a novel input feature vector according to what class your nearest training vector is. So you start off with a bunch of training data. Here's your training data, blue blobs and red blobs in this case. And you simply assign a new input vector to whichever is closest. So if your new input vector lands here, you're going to classify it as black. If it lands here, you'll say it's in the red class. The decision boundaries are lines here, boundaries that are equidistant between class centroids. This is a thing called a Voronoi tessellation of this feature space. And if you have enough training data, then the decision you can see here, the decision boundaries here are already pretty complex. If you have enough training data, then they can be as complex as you like. And you can have arbitrarily many classes and just assign the input vector to the nearest class vector. This makes it unnecessary to do any fancy modeling. You can just use the data. It's the simplest way of using the data. There are some disadvantages to it, but we'll get onto them later. So with unlimited training data, if you have unlimited training data, you can show that the average error rate that you achieve with a nearest neighbor classifier is less than double the Bayes rate, which is the best achievable error rate, going back to what we were saying about how you choose your discriminant functions optimally. This was shown way back in, that's 52 years ago. So that's okay, it's good, but the problems with it are that, firstly, you need enough training data to cover your input space, and the higher dimensionality the input space is, this D here, the more training data you need. It's a thing called the curse of dimensionality that you may have heard of. And the training data also needs to statistically represent the input data adequately, or you're not going to do as well as you could. As for computation and memory required, if you're dealing with d-dimensional vectors and you have n training vectors, here they are, n training vectors xi. For each of those, we need, when a new input vector arrives, in principle, you need to compute the distance between your new input vector and every one of these training samples. And if these vectors live in a d-dimensional space, that means that you're doing d multiplications, subtract and square. So you need to do d multiplications for that, and then to find the closest class training vector, you need to take the minimum of these squared distances that you computed. And if you do that, the computation that you need goes up with the product of d and n. So this big O here is order. It goes up of the order of d times n, which can be rather large. The more training data you have, the bigger n is, and the more dimensions this data lives in, the larger d is. So that can be a problem. The k nearest neighbor classifier, or KNN, is an attempt to smooth out some of the noise in a single nearest neighbor classifier. So you now classify a novel input vector according to a majority vote among the classes of the nearest k training vectors. So in this case, for example, here's our input vector x, and these 5 points within this circle here are the 5 nearest training points to it. So k equals 5 in this case. And in that circle there, it's kind of difficult to see with these tiny points, but 3 of those training vectors are black and 2 of them are red. So in this case, black is going to win the majority, the competition, and that X is going to be classified as black. So this may be better than doing a single nearest neighbor classifier when the classes overlap like they do here, because you reduce the amount of noise. It reduces the effect of outliers, i.e. non-typical training data. And you can force the error rate to further approach the optimal Bayes rate, the minimum error rate, if you have unlimited training data as k increases. So in practice, it's a trade-off because this requires more computation than just finding one nearest vector. So it's a trade-off between computation and accuracy. Here's the red line down the bottom here. This is the Bayes rate. This horizontal axis is the Bayes rate. This is a kind of x equals y line up here. And the cover theorem from 2 slides ago says that you can, a regular single nearest neighbor classifier can do better than twice the Bayes rate, which is this line here. And as you increase the number of candidates in the majority vote, you can get nearer and nearer to the optimal Bayes rate there. But the conditions for that to hold are that this is as your training, the amount of training data you have gets arbitrarily large, as the number of dimensions, not the number of dimensions, the number of data in the vote, the majority vote gets large, but the ratio of them goes to 0. So these are quite stringent conditions. Okay, you don't need to worry too much about that. There are ways that you can reduce the computation in a k nearest neighbor classifier. There are 3 main ways of reducing it. One is to only do some of the distance computation. D here is the number of dimensions that these vectors live in. So you start with j equals 1 here, and for each dimension, calculate this difference and then square it and add it to your total. But the moment your total partial sum here exceeds the current minimum distance or squared distance, you don't need to carry on. You already know that that input vector is not going to be the closest. So that's one way of doing it. Another way of reducing the computation is to pre-index your training samples. For example, partitioning the feature space or the training data. For example, if your input vector is this blue cross here, you might reduce the computation by only testing samples within this quadrant that it fell in, so you don't have to do all the computation for these other training data. Of course, the risk that you run in that case is that you'll miss the actual nearest neighbor if it's there. So again, it's a trade-off between error and computation. Okay. Third way of reducing the computation is to edit your data set in advance. For example, by removing samples that are surrounded by all neighbors of the same class. For example, this red guy here is surrounded only by red cells, so that can be removed without affecting the results. Another way of doing it is to remove samples near the boundary that are considered to be noise and simplifying the boundary. So here, this incursion here into what looks like the red space, you might think that this blue sample here could be noise, and that actually a smoother boundary like that would be better. So that's an example of something you can do. Okay. Yeah, if you remove this Wilson editing, this involves removing samples of different class from the majority of their k nearest neighbors. So let's see, in this case, we've got some blue samples here surrounded by a majority of red there. So those 2 points there can be ignored if we assume that they're likely to be noise. And then you can get the same result by using a single nearest neighbor classifier on this. Okay, so that's that. Issues with this kind of classifier include overfitting and generalization. Typically, we partition the training data into training and test sets. So you use some of the data to set up the classifier and then use the rest of it to test how good the classifier is. So train the system on the training set and then evaluate performance on the test set. A problem with any kind of classifier is that any system will perform better on its training data than on the test data. That's true even if you sample both of them from the same probability distribution, and that's called overfitting. It affects all systems that are trained on data. It's usually worse if there's less training data. The less training data you have, the more likely you are to overfit your classifier to it. If there's noise in the training data, that causes problems. If you try to learn more parameters of some model, for example, when you decide where you're going to put your boundaries in a parametric classifier, if you try to learn too many model parameters or use more complex decision boundaries for nearest neighbors, you can get overfitting. It's nearly 6 o'clock, so I'll just go through this overfitting example and then we'll leave it for today. So we're going to do an example where we fit an nth order polynomial So that's a polynomial like this with coefficients am to a0. So these are m plus 1 parameters, a0 up to am. And it's an mth order. The highest power of x here is m. And we're going to fit this polynomial to these n data points, x1, y1 to x1 to xn, yn. If we do that, the error in our approximation is going to be, for each of these points here, we subtract from yi the value of this polynomial at the value xi, square it, add them all up, or take the average here, and then take the root. So RMS error is, this stands for root mean square, in case you're not familiar with that. So here's an example of some data. This is from Chris Bishop's book. This book is much newer than the Duda, Hart and Stork book. It's also much more difficult, but it has some useful examples in. So here we've got some data samples, these blue circles, x, y, and we're going to model these data samples as being from a noisy sine wave. Now, we don't know that they're from a sine wave. All we're given is the blue circles, and we're told to fit a polynomial to them. So these data come from this sine wave plus noise. The noise is in the vertical direction here. So each of the y values is the sine wave value, sine of 2 pi x, plus some kind of noise here. This is some kind of Gaussian noise with small variance. So we've added some vertical noise to each of these y values. Okay, if you try to fit a single parameter, if I go back to here's our polynomial, single parameter, a0 only. Try to fit a single parameter to this data, you just get this constant here. If you try to fit a linear polynomial here, so this is something, so you're approximating y as something times x plus some constant, you get this line. This line is the best fit to these points. It's still not a very good approximation of this sine wave. Now if you fit, this is a third order polynomial, so this is a cubic polynomial, and it's getting much better. It's getting closer to the sine wave. If we go to a ninth order polynomial now, so we have 10 parameters to play with, we can fit this polynomial, this red polynomial, exactly to all the data points, like this, which sounds like it should make us happy, but actually it shouldn't make us happy because of the wild variations between the data points. So although this approximation is good, very good at the data points themselves, it's going to be very bad probably for novel data points. So with m equals 9, we've exactly fitted the polynomial to the training data, and the RMS error on the training data has dropped to 0. But the reason it's dropped to 0 is we have overfitted the function, our approximation, to the training data, which means that the approximation is going to be poor for new novel test data. And it can be said in general that overfitted solutions have poor generalization. That's the problem with overfitting. So in this case, we gradually increased the order of approximation of this polynomial, and the error on the training data gradually reduced, and the error on novel test data gradually reduced, until we got to here when we fitted this ninth order polynomial exactly to the training data, at which point the error on the RMS error on the novel test data suddenly increased. And this is the results of overfitting, poor generalization. Okay. And this is a problem in any type of classifier if you overtrain it or overfit the data. So to go back to the salmon and sea bass example, so we've got this, you may remember we tried fitting this linear boundary, and this seemed to work reasonably well, but there are still some errors. There's still some salmon the wrong side of the line and some sea bass the wrong side of the line. So you might think that a more complex boundary would fit better. So how about something like this? And well, yeah, this boundary does fit the training data better. In fact, it fits the training data very well. But again, because it's overfitted, if a new sample were to arrive where that question mark is, it's unlikely to be correct on average for positions of the new data. Okay. I will go on for just a couple of seconds more. So how can we reduce or avoid overfitting? One way is to select the model well. Choose a model that's complex enough but not more complex. That's the main lesson. And that principle is known as Occam's razor. You may have heard of Occam's razor in philosophy, meaning don't overcomplicate explanations. There's a thing called k-fold cross-validation that's often used to evaluate classifiers, where we partition all the available data randomly into k sets, use k minus one of them for training and the other one for testing. Do that for all the k partitions of this data. Keep rotating through the data like that. Average the test error over the k partitions. In an extreme case, if you've got k data points and you use all but one of them for training, the other one for testing, this is called leave one out cross-validation for obvious reasons. Let's see now. Right. This would be a good point at which to leave it, I think, until tomorrow. We'll carry on from this, because this is a slightly different conversation after this, so we'll carry on from this point tomorrow. Unless everyone really wants to keep going now. But this is a fairly convenient place to stop for today. Yeah, you can ask me questions now or tomorrow or next Wednesday or by email anytime. Okay. All right. Thank you. Thanks for coming.